Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Jenn Carter with us today. Hello, Jenn.
Hi, thank you for having me.
Well, thank you for agreeing to talk about your very awesome article here, which we'll get to in a second. And Jenn, what's your geolocation? Where are you located?
I am located in Selinsgrove, Pennsylvania. I work out of Susquehanna University.
Very cool. Very cool. Summer must be in full bloom, I assume, and you've got some very lovely plants over your right shoulder there.
I have a whole set of jade plants. Those are the ones with like the smaller leaves. And
Yeah.
then the ones in the terracotta, like here
Uh-huh.
and here, those are apparently mini rubber tree plants. They're not related to the rubber tree at all, but that's what they're called. And they're
Oh.
extremely happy right now. They're starting to put out seeds and they're having a great time this summer.
Oh, very good. That is awesome. Very cool. And besides rubber plants and assorted botany experiments there, what do you like to do for research, Jenn?
For my research, I am looking at exoplanets.
Cool.
That all started back in graduate school. I just knew I wanted to do space stuff.
Hmm.
And my advisor, the only person doing space stuff at UAlbany at the time, was Kevin Knuth. And he
Oh,
was
yeah.
looking at exoplanets and working on something called ExoNest with one of his other grad students. And my project was reflected light
Cool.
because we had found an exoplanet, Kepler 91b, and the data they were looking at suggested that maybe there might be a Trojan planet, so a companion with the same orbital period but slightly offset.
Uh-huh.
But the output suggested a night side temperature higher than the day side temperature.
Wow. Okay.
Yeah, that doesn't make sense. So they flagged it as a false positive. And we thought that maybe it might be a mix up of thermal light with reflected light.
Okay.
And we found another paper that suggested that Kepler 91b experienced 70% of illumination. So we have light on the anti-star side, easy to
Yeah.
mistake for thermal light. Um, so here we are now. I just
And one may
kept
wonder
rolling
how
with
that
that.
happens, and we're going to find out very
Oh,
soon.
yes.
Very cool. Very cool. And that is going to bring us And that is going to bring us to this very lovely article, which I will bring up here. And there we go. This is an AJ. It is open access. It's the open access era, people. Go grab a copy for free. Hyper illumination of exoplanets, analytical and numerical approaches. And Jenn, take us away.
All right. First, I want to start off by thanking my co-authors, Rossini Pereira from the University at Albany and Michael Way from the NASA Goddard Space Institute, as well as the Uppsala University.
Very
Um,
good. Cool.
I think the first thing I might want to start off with is just flagging that there's a lot of symbols in this article. And if you're following along, you want to go towards the appendix. Table 4 has a list of all of the symbols we're going to be talking about today. I'm also going to try to define them as we go
Mm-hmm.
along.
Mm-hmm.
But just so you know, it's all written there, so you don't
Very
have to
good.
memorize them yourselves.
Awesome. I love symbols of tables from papers like this.
It was necessary.
Absolutely. Okay.
All right. So, starting off, what's the whole point of this? We want to characterize exoplanets. We want to know how hot they are, how big they are, what the temperature distribution is. Reflected light can give us information about whether or not there's a continent here or an ocean there.
Okay.
But all of that starts with the radiation that's incoming from the host star.
Yes.
That's what we're looking at today.
Okay.
Most of the time, any given planet is about 50% illuminated
Mm-hmm.
and 50% unilluminated. And this follows from what's called the plane parallel ray approximation, where you just have rays of light smacking into your planet.
Mm-hmm.
But if a planet's very, very close to its host star, you can't really treat it like a point source anymore, where
Okay.
those plane parallel rays would be coming from. Instead, you really have to take into account that finite angular size.
Cool.
So
Very good.
it's not a
Okay.
point, it's finite.
I'm with you. Mm-hmm.
And this leads into things like reflected light that's been looked at by a lot of researchers, people looking at light curve data, people attempting albedo mapping. And one of the things I think is cooler is looking at climate modeling and atmospheric modeling.
Yeah.
And this comes into effect, this incident radiation, because that's what sets the energy balance to start. What goes in is where you start.
Yep.
And an interesting paper I saw too was that one from 2011 about Cohort 7b,
Oh, okay.
where they pointed out that if you don't use the plane parallel, like rather if you use the plane parallel ray approximation and don't account for the finite angular size,
Yeah.
you end up with not enough. It underestimates the temperature in the penumbral regions, which is that region that receives partial illumination.
Cool.
To get started on this, it's really helpful to look at the reflection effect for binary stars. The stars actually reflect light between each other. And some early papers in the 40s and 50s and into the 60s looked at this reflection effect. And it's starting to also be incorporated for exoplanets in the context of this paper in Lugre et al. In their Starry Code, as well as the transit and light curve modeler by Zismadia et al. 2023.
Right. Okay.
And everybody takes slightly different approaches. My approach is to stay analytical for as long as we can and then start using numerical methods where we cannot be analytical. All right. So looking at figure 1, we see that plane parallel ray approximation. Yeah, throughout the paper, I try to have the star on the left side and the planet on the right side. OS is the center of the star, S for star. OP is the center of the planet, P for planet. Their separation is RS.
Yes.
And we can see this is clearly not to scale because we would not have a plane parallel ray approximation applying for this sort of system. Now, often gamma prime, that angle on the right there, is treated as the angle of incidence for the plane parallel ray approximation because you assume all of that light's coming in just parallel. Whereas what we're going to use for the angle of incidence is psi, that E looking thing. And we'll see that that angle of incidence changes depending on where you're looking at the star. And we're going to start simple. We're going to start by actually just thinking about what parts of the planet are illuminated and approximately how much. So we're looking at the illumination extent. So equations 1A, B, and C.
Let's take a look at that. Illumination extent, section 2.1. Here we
right
go.
there.
And here's our angles. Straight out geometry there.
Oh yeah, a lot of this is going to be geometry.
So
eta is the polar angle we're measuring from the pole away from it. And eta full, this marks the extent of the fully illuminated zone, which we'll see in figure 2.
Let's go down and take a look.
Yeah, are we able to kind of get both? Yeah. That'll be pretty close. Yeah.
Well, why don't we just go like that and then we'll zoom in as need be.
Perfect. So eta full marks that yellow portion on the spherical cap of the exoplanet facing the host star.
Got it. Okay.
Points there receive light from the entire apparent disk of the host star, which is not the hemisphere facing the planet. It's slightly smaller. It's always going to be smaller. Eta UN or eta un, that marks the edge of the unilluminated zone. And you'll notice that black region is beyond the hemisphere of the planet facing the host star.
Beyond that point.
Everything between those two regions, the orange and the maroon regions, that's the penumbral zone. Points there are experiencing sunset or sunrise, basically. Less than the apparent disk of the host star is visible. You can imagine it's setting below the horizon. Now, Eta Pen is generally a small angle, the smallest of them.
Okay.
And that marks the penumbral subzones, PZ1 and PZ2.
Okay.
The first penumbral zone is the one facing the host star, closer to it, I should say, in orange. That one sees more than half the apparent disk. And the maroon one, PZ2, sees less than half the apparent disk.
Yes.
The
Okay.
only reason we need that angle is if we try to determine the illumination within the penumbral zone and treat those two as the same.
Yep.
The integration limits are not appropriate. The integration limits in one zone is different than the other when you try to take an analytical approach. You can learn more about that in Racine Pereira's recent paper with Kevin Knuth,
Cool.
as well as some of my previous work. We're mostly going to focus in on general approach rather than that nitty-gritty detail.
Okay.
But thinking about this sort of broad splitting up of the zones on the planet, we can start doing some work and think about what sort of planets might this apply to. Should we worry about extended illumination? And some of those are listed in table 1.
Cool.
So we have planet name on the left, semi-major axis, planetary radius,
close,
star radius. Yes, very close. And then a couple of things that I have calculated. So everything to the left of sigma XS is stuff that you can look up from the NASA Exoplanet Archive or other sources, the papers they pull from. Now, sigma XS is the surface area in excess of 50% that is experiencing illumination on these planets, which we can calculate in part from equation 2, sigma lit. That's the surface area receiving any light.
Yes.
And naturally, you see as that star-planet separation, RS, the lowercase rs increases, that whole term on the right just disappears and we approach 1/2.
Yes.
We also see that as the stellar radius becomes larger, capital RS, we end up with more and more illumination. So bigger star compared, importantly, to the size of the planet, right? RP, that radius of the exoplanet. So it's this balancing act between star-planet separation, the size of the star, and the size of the planet.
Cool. Okay, I'm with you.
Yeah. Probably the biggest contributor is the scaled star-planet separation, scaled to the radius of the host star.
Yeah.
Stars are bigger than planets. Now, what's interesting about this table is it has a variety of exoplanets on it. We have super Earths, we have hot Jupiters like Kepler 91b and Kelt 9b, and we have potentially habitable exoplanet TRAPPIST 1d at the very bottom. Now you notice that one, since it's further away compared to the size of its host star, has very little excess illumination, only 1.2%.
Right.
But if we look at the last column, which is the calculated surface area that is above the surface area we would expect to receive light, it's pretty big.
Yes, comparatively.
And it's slightly larger than the area of India on our own planet. So this takes up more than the area on Earth. On Earth, oh goodness, what was the penumbral zone size on Earth? 0.5% or so?
Yeah, something like that. We get
a little bit.
Cool.
More might matter a lot. I'm very interested in learning what happens when we apply this model to climate models.
Yes.
That's probably the next goal, but we're getting ahead of ourselves if we're thinking next goals. Now that we've gotten a little bit of a sense of the variety of types of exoplanets that we should think about and just how large that excess illumination can be, we're looking at 20% for some of these planets. We should start talking about how do we calculate it.
Okay.
How do we calculate the illumination? And we're going to start simple with a point source.
Point source, always a good thing.
Always start with the point source so we can set up our geometry. And then the idea is, okay, you figured out a point source, add them all up, spread the points on the star and add it up.
Yep.
That's the main theme here, but we do have to be a little careful on how we do that. So equation 3 is the illumination IP, or the intensity, IPT, I should say. So I for intensity, and the subscript is telling us the model of the star we're using. In this case, a point source. And I'm going to stick to that sort of theming with the subscripts.
Okay, cool.
Pi s is the flux per unit normal coming from that host star. Rho, if we look at figure, what is it, 3?
Yeah.
Yes. Rho separates our point P on our planet from the illumination source.
Yes.
All right.
Mm-hmm.
P is that vector from the center of the planet to point P, so it's that normal.
Bing. Yes. Okay,
So
good.
the intensity of light received at point P due to a point source depends on that dot product between rho and P, or at least their unit vectors.
Okay, yes.
So it's cosine of psi, where that really is our angle of incidence for a point source.
Okay.
The rest of this figure is setting up some other angles. We have theta I, which is very, very close to the angle of incidence, right? It's the angle between P and the vector from the center of the planet to the host star, that star-planet separation vector.
Yes.
For large planet separations compared to the size of the, for large star-planet separations compared to the size of the planet, var theta I and psi are about the same. And it's var theta I that Starry uses in its code for the extension they put in from dealing with thermal mapping towards reflected light.
Okay.
They use that var theta I when they're looking at the point source approximation.
Okay.
For now, we have our coordinate system centered at the planet, center of the planet, and the illumination source is located at XS, YS, ZS.
Yes. Boom, boom, boom.
So the coordinates are shown on equation 4a and 4b for both the point P and the location of the center of the star. And they're basically spherical coordinates with a few rotations that just make the figures in our results section a bit easier to handle. What this works out to in the results section is Z is out of the page. If we set it all this way, and what we're going to do is we're going to take our illumination source and put it on the Z axis. That's the idea. Yes. And the reasoning behind some of these angles. All right. So we can also relate cosine psi to all the different variables shown there. We can do this using equation 5 and using equation 6, which follows from Luger et al. 2022 in equations A9 to A12, it looks like. We can relate cosine psi to cosine var theta I in the calculation using the rotation of the y coordinate and the theta s and all those things shown in the paragraph. It's just a little bit faster than doing this as a series of dot products.
Fair enough.
But me personally, I find it easier to understand the dot products, so that tends to be what's written down.
Okay, good.
All right, so how do we calculate the light? Well, we look at equation 7.
Yes.
And we see that the intensity as a function of cosine psi, or basically your point on the planet, is inversely proportional to rho squared.
Yes.
We've rederived the inverse square law.
Yes.
Fantastic. But that's important. You know, we have to check. We have to check and make sure that along each step of the way that we're making sense.
Yeah, it reduces properly. Yep.
Exactly. And cosine psi again reduces to cosine var theta I for large planet separations. And in a later figure, figure 4, which we'll get to soon, we'll see that I start basically calling that gamma prime, that angle between P and RS, because it follows the earliest papers I read
Yes.
So we do a little bit of a replacement later on.
Mhm.
And importantly, we see that the plane parallel ray approximation is basically this point source approximation if the point's very far away. You can think of this as spherical wave fronts becoming basically planar as you increase that distance.
Yes.
Again, it all follows from towards what people have been using. Now we're just going to start being a little bit more precise and look at the extended source case. So
Yay.
instead of a point, we have a sphere.
Okay.
We're dealing with spheres today. One could extend this to non-spherical sources and non-spherical planets, which I think is one of the next steps. But today we keep it a bit simpler. We look at spheres.
We'll come back to that. Okay.
Oh, yeah. So instead of dealing with our point source, we're now looking at equation 9. And we've written this as a differential instead, right? Our goal is to figure out the differential intensity at point P, DIP, due to the light coming from point Q, IQ.
Yes.
All right. There are some angles involved, right? We see that dot product again with a prime because we're looking at a slightly different vector now, rho prime instead of rho. And we also see that our differential involves the differential solid angle of Q viewed from P. That's what those subscripts are meant to indicate. It's the differential solid angle of Q as viewed from point P on our planet.
Okay. Good.
Okay. So our first big step is to figure out how can we calculate that in terms of the surface area, the surface elements, I should say, of the host star. We want to get this in terms of dA, and that's equation 10.
Okay.
Now,
okay.
And can we get it so we can see figure 4 sort of at the same time, or at least partially?
Yeah, we'll zoom out. How about there?
Perfect. All right. So you see that dot product in the numerator of equation 10.
Yes.
That's the dot product between the line connecting P and Q, rho prime, and the normal of point Q.
Okay.
Right. So yes, we see it ends up basically becoming cosine theta prime.
Okay, and here's rho prime for those.
Yeah.
Need the picture. Okay, good.
Yeah.
Yes.
And the minus sign is there because it needs to be rho prime and dr hat are in different directions. And we really only care about cosine theta prime.
Okay.
And I did this because I wanted vectors to largely come from OP or P.
Yes. Okay. I'm with you.
Anyway, the numerator of equation 10 works out to being the projected differential surface area.
Yes.
So we have to account for the foreshortening of area elements of Q.
Okay.
So here we have to realize that we're not looking strictly at points on the star. Each one of these points is representing a surface area element.
Yes.
They are finite and they can be foreshortened. And that's what equation 10 lets us do, is we also account for that separation between points P and Q as well, using now rho prime instead of rho, where rho points from P to the center of the star.
Yes.
Because before, when we were looking at a point source, what we were doing is basically putting that point source at the center of our star and neglecting its size.
Right.
Hence that being rho, rather than the distance between P and Q being rho. Now that's rho prime, because I wanted it to still be rho.
Thank you for that clarity.
Yeah. Okay. Now we do some geometry.
I love geometry. Great.
Yes. And what geometry are we doing? We want to build up equation 11, basically. So we still have that cosine psi that accounts for the projection of the light coming from Q towards P onto the normal of P. Good. Now we also have this cosine theta prime to account for the foreshortening of our area elements. If we know what IQ is, that is the intensity coming from point Q. We can add them all up. Yes. We also have to calculate things like rho prime.
Nice, very nice.
So this looks very similar to that inverse square law with some added bits to account for the fact that this is not a point. It's a sphere.
Yep.
And as always, if we take this to large planet separations, the size of the star becomes unimportant. Cosine theta prime approaches 1.
Yes.
Cosine psi approaches cosine gamma prime, and we return to the plane parallel ray approximation.
Cool. Very good.
All is intended.
Very good. Okay. Cool.
So equation 11 is our kind of root equation going throughout the rest of the paper. And now we start thinking, how do we solve it?
Mm-hmm.
So analytically, what do? Well, we need a way to write dA in terms of the variables on the host star.
Yes.
So we need to know the coordinates of the parts of the host star, and that's equation 12. That's the difference, drq, from the center of the star to each of the q's. And we mostly just care about their direction, because we know they're always going to be a distance rs, capital RS, from that center. Because we're dealing with spherical stars.
Orientate P.
Yes.
There's P. Okay.
There's
good.
P.
I'm with you. Mm-hmm.
Good. Right. That's the other important part. We're shifting our coordinates to be centered at P instead of the center of the planet, because we're doing an integral from the point of view of point P over all of the Q's visible from point P.
Yes.
So you can imagine the z-axis is now aligned with rho.
Yes.
And we have omega goes around rho.
Yes.
And theta q is that latitude.
Yes. Okay.
Yep. So we have all of the angles we need.
Cool.
From there, we do a whole bunch of geometry. I don't want to necessarily walk through each step. It's an application of the law of cosines, law of sines, some dot products. And eventually this takes us to equation 17.
Right.
This is the intensity of light received at point P, which we can describe in terms of the angle alpha. You'll see it depends on how big the star is. And two integrals that I labeled A and B, because I could separate out sine alpha and cosine alpha, which are constants on the integration of the host star. So alpha is similar to that angle of incidence, but not quite. Importantly, it only depends on your location P on the exoplanet.
Okay.
Yeah.
Is there let me just random question. Is there something physical about the decomposition into A and B? Does that have a physical interpretation?
It does end up having some physical interpretation.
Okay.
If you look at A and B, you'll see that B includes this. It doesn't include a cosine omega term, whereas A does.
Here's cosine omega here.
Yeah. So we're thinking about that rotation around rho.
Got it.
Equation 18b.
Yeah.
The B part of our integral doesn't include bits about that rotation, or rather it just has d omega. That's the inclusion. Whereas A does include kind of that projection, I guess, on the cosine on the z-axis, on the rho axis.
Yes. Okay.
Yeah.
Good. I'm with you. Okay. I didn't mean to take you off track. I was just curious.
I hadn't thought about it before in a while. That was a great question. Thank you. Also, the nice thing is when we're in the fully illuminated zone, which we'll see in a sec, equation B is 0. So it's also just very convenient that we can just set 1 to 0. But before there, I want to talk about how we might approach calculating this light in the penumbral zones. Like the fully illuminated zone, we have this nice spherical cap. It's nice and symmetric.
Right.
In the penumbral zones, we're taking slices off of it and it's ugly. But we can define how much of a slice we take off in terms of this angle lambda, which you can see in figure 5. All right. That is
lambda down here.
Yeah. So we take our horizon at P, which is labeled as that long dash dot line, and it intersects the disk of the host star at H, right? And H, that forms a plane. And we can define the angle of that plane in terms of lambda from rho. And that's convenient because lambda can be related to our latitude coordinate. And we can set integration limits on it.
Cool.
The struggle is finding omega in terms of lambda and having an integral that is analytical.
Okay,
It's not.
believe that.
So instead, we end up using either a series approximation or
Okay.
numerical integration as we do in this paper.
Okay.
Now, anyway, if you're interested, equation 19 is that calculation of lambda, the geometric depth of the eclipse. And it depends on your location on the planet from alpha
Okay.
and rho. Alpha and rho probe the location of P on our planet. And it depends on the size of the host star, RS. Right? For very large star-planet separations, lambda becomes something simple that equates to the penumbral zone just doesn't really exist.
Yes.
Yeah. And you can see that too with those eta angles from previously. If you look at those, you'll see for large star planet separations, the fully illuminated zone and the unilluminated zone just meet at 90 degrees.
Correct.
Or rather, 90 degrees latitude, 0 degrees polar angle. And
Yes.
the penumbral zone just doesn't exist.
Right, because it's
Yeah.
top. Okay, cool.
So that's how we would approach an analytical solution within the penumbral zone. We're going to leave that for future work and focus on the fully illuminated zone, because I did want at least one analytical solution, if at all possible, to compare the numerical output with and tell how good is this numerical integral?
Right.
How many points on the host star do I need?
Mm-hmm.
When does it matter? So for points within that fully illuminated zone, you see the entire apparent disk of the host star, and it forms like a spherical cap aligned with rho. So at the substellar point, we have a spherical cap that's just aligned with RS.
Yep.
And then it rotates. That spherical cap ends up rotating and changing size.
Cool. Okay.
So that has to set our limits of integration. It ends up being more convenient to look at, it's integral A that evaluates to 0 because it has cosine omega, and integral B that sticks around.
Oh, right. That was opposite.
Yeah. I mixed the two up.
All good. No, I didn't catch it. All good.
Yeah.
Okay.
That's okay. It's written in the paragraph here. So we've caught up. Yeah. All right. So then we're left with an integral over theta, and it's a little easier to write this in terms of rho prime, which is what equation 21 ends up doing. We do a substitution of sine theta q d theta q in terms of rho prime. We're keeping in mind RS and rho are constant for points P. Rho prime is what changes, and it has a range between rho and minus RS, the size of the host star. And then there's this maximum value where, from the point of view of point P, you've got a line that's tangent to the host star. So that's what that upper limit ends up working out to. Now, in principle, we could do this for any sort of limb darkening model you want. I know it's analytical for both zero limb darkening and linear limb darkening because I've worked them out.
Right. Cool.
It's likely for any power law to be perfectly fine.
Mm-hmm.
We're going to keep it simple today, though, and just treat the light coming from the host star as constant.
Yes.
Because we're just getting this working. But this is definitely extensible. And the integral comes out as equation 23. And we combine that with previous equations to get the intensity within the fully illuminated zone.
Yes.
Equation 24.
Yes.
And you see it depends on that cosine alpha and the separation between your point P and the center of the star, which is rho.
Yes.
As well as the size of the star.
RS.
To make things even simpler, we're going to end up doing this in units of stellar luminosity. So if we scroll down a little bit for equation 26, we get that same idea where we make a substitution for cosine alpha and rho squared to get this in terms of cosine gamma prime. Because that makes it simpler to see that we again return to
Yes.
the plane parallel ray case
Yes.
if first the size of the planet is small compared to the star planet separation.
Yes. Cool. Yes, cancel,
Yeah,
cancel.
it just cancels and
Boom. Okay, I'm with
Yeah.
it. Mhm.
very good.
Indeed.
That is the only portion of the planet, that fully illuminated zone, where we have an analytical solution to use as our check. So we're going to see that show up again in some intensity maps in our results section. But before we get there, how do we do this numerically?
Yeah.
Because we need to be able to do that within the penumbral zone. The unilluminated zone is easy because it's just 0.
Yes.
Yeah.
I love 0.
It's just put in 0. All right. Let's start off with how do we do it in this paper? And then we'll talk about how Starry does it, because we're going to make a comparison between the two.
Okay.
Within this paper, we are going to distribute n points uniformly on the effective disk of the host star.
Let me just go back to 11. So this is the one we are going to be solving analytically or numerically
Yes,
right here.
correct.
Okay. Okay, I'm with
Numerically.
you. Yep, numerically. Okay.
All right. So we want all of our points on the star. We have a disk, distribute the points evenly on our disk, and then pop it out into a sphere.
Yeah.
Well, a spherical cap, I should say. All right. This means that the differential area of each one of those points is about 1 over n if you're not accounting for foreshortening. This is also following how Starry distributed their points for their intensity maps, because I wanted a good 1-to-1 comparison.
Yes.
We're going to call this I extended, EXT in the subscript is for extended source model.
Okay.
And then cosine psi cosine theta prime indicates which of the cosines we are taking into account, not setting to 1.
Right.
I also just call it I finite sometimes. Now,
Okay.
Starry also starts off with a point source approximation, which you can see in equation 27. So I point, because we're looking at a point, and Starry using the Starry method in those subscripts. We see that they approximate the size of the planet as small compared to the star-planet separation. So that in the denominator, you see RS instead of rho squared. And in that max function, you see cosine r theta I instead of psi.
Yes.
Which again are approximately equal for cases in which RP is less than RS, the star-planet separation. Now, to extend this to the extended spherical source, we distribute our points and we add up equation 27 with a small change. We can't just keep looking at RS. We have to look at what I believe I labeled as RQ. Yeah, up at the top there. Yes, RQ.
Yes, okay.
So you know what that offset is from the center. You just add them up and there you go. That's your extended source case. And in future plots, that'll be labeled as I extended, comma, Starry.
Okay.
As another comparison, because I noticed this, I wanted to know how important having that foreshortening of the differential areas of each point Q was.
Yes.
So we have equation 28, which is an extended source equation, but only accounts for cosine psi, that angle of incidence, and neglects that foreshortening.
That would be interesting. Okay.
Yes. Like I said, I wanted to know at first just like why were my results so different than Starry's, and over time digging through the source code and playing with it, this is one of the discoveries I made.
Cool. Very good.
On the differences in approach.
Good. Okay.
All right. That's all the theory.
We are armed and dangerous.
Results. And the results we're going to focus in on today are some intensity maps of 3 exoplanets as examples. We're also going to look at some subtractions on certain parts of the planet. And we're also going to think about, well, what happens if you change the number of point sources that we pop onto the star?
Yes. Yes.
Yeah.
Convergence.
That's the main goal. Yes. Is it convergent? And to what?
Well, fair enough. May
These
not
are
be what you think it is.
indeed. Um, so all of these intensity maps are going to be in
Okay.
units of the stellar intensity in parts per million because it makes the numbers more digestible. So I think we can probably look at figure 6.
Yeah, let's take a look.
Yeah, and table 2.
Okay, let's do figure 6 to start. I'm going to zoom out a little bit. Okay, here we go.
Okay. So these are intensity maps using 6 different methods of calculation for the hot Jupiter Kelt 9b.
Okay.
On the right, you see the color bar. All right. So yellow is most amount of light, dark blue is no light.
I'm with you.
And this is all, that color bar is shared across all 6 of these subplots. So the brightest yellow is the brightest point. And we also have our contours shown as those dotted white lines.
Yes.
Right. So 100% would be the most intensity across all 6 maps.
Okay. Okay. Yes.
Now, each
Mhm.
each one is labeled in like a subtitle for the method used.
Uh-huh.
On the very top left, we have the extended source case for starry.
Yes.
And next to that, we have the extended source case where we only include the angle of incidence.
Okay.
Right? None of that foreshortening.
Nope.
Next, in the middle left, we have the method described using equation 11.
Yes.
Extended source includes angle of incidence and foreshortening.
Yes.
We have our analytical model, I full.
Yes.
And you'll notice it only exists within those dashed black lines.
Correct.
Because that's the only region in which that equation applies.
Correct.
Everything else is either the unilluminated zone or the penumbral zone, and we can't use the equation.
Mm-hmm.
So that's kind of our test case. We always want to see which method matches that well within that region.
Mm-hmm.
Finally, on the bottom, we
Okay.
have our more general approximations. We have the point source case as done by Starry, and then
Yes.
the plane parallel ray case as generally used.
Okay.
So what do we see here? What can we notice? Well, if you look at the fully illuminated zone 1 at that substellar point, which is at the center of 0 latitude and 0 longitude, you can imagine you're out of the screen and you're in the host star looking at the planet.
Yes.
Yes. It's a lot brighter for the starry case. There's more light there than we would expect from our analytical method. And if you do a subtraction, you'll find that the greatest amount at that substellar point is about 119 parts per million.
Okay. Okay.
In units of I star.
Right. Right.
Right.
Probably about factor 2.
Something like that.
Yeah. Uh-huh.
And other things we notice that extended source case with cosine psi only, just that angle of incidence, looks a lot more similar to the extended source case for starry than the fully illuminated zone. This indicates to me that that's a big contributor to the difference, but probably not the only thing.
Right. Very good. Okay.
In addition, you'll see that our numerical method from equation 11 in the middle left is visually a pretty good match, at least visually. And honestly,
it's really just the amplitude.
Yeah. And you'll also notice that like the rate at which the amount of light changes is different for that starry method versus the method shown in the middle left, right? We end up with a greater fall off of light within the penumbral zone. So that's beyond that black dashed line and before that 0% contour.
Got it. Okay.
Yeah.
Okay.
So there's some places where we have overestimations and some places with underestimations, at least comparing to each other.
Right.
And that's Kelt 9b.
Interesting.
And I chose this planet to explore in part because it was one that Starry looked at, Luger et al. In their paper. And it was a really great way to make sure I understood how to use Starry.
Just a reminder for people, this was Celt 9, where we have about a 15% excess.
Yes.
Okay, good.
I'm with
now
you.
it
doesn't have the most excess, but
No,
it actually
no.
has a very large fully illuminated zone and compared to some other planets. I don't think I listed it that size anywhere, but it's something one could calculate using something similar to equation 2. Actually, it doesn't change too much from that.
Okay.
The fully illuminated zone is it has a 1/2, and then in parentheses it's 1 minus something involving those same terms, but I don't remember the combinations right now.
That's fine. That's simple enough one could do offline.
Yeah.
Okay, very good.
That's
so
some geometry.
There's Celt 9, yeah.
Yep. Now, figures 7 and 8 are similar, but for 2 other exoplanets that are listed in table 2.
Yeah.
So we have the hot Jupiter Kepler 91b, which is of interest to me because it has a lot of illumination, 70% illuminated. And I mentioned previously, we had some questions about it in the context of a different paper that some of my colleagues at UAlbany had done. I also wanted to include a planet completely different than the other two in the form of TRAPPIST-1d, because longer term, we really want to see how this extended source might affect climate models, in particular for potentially habitable planets, which are often close to their host stars because we're finding them around M dwarfs.
Okay.
All right. Looking at figure 7, it's very similar to the previous figure, but this is for Kepler 91.
Okay.
Key differences. The maximum intensity is different. It's not as big. It's not as great.
It was 300 up before, 350.
Yes. So even though this experiences a greater surface area being illuminated because of the balancing of things, it's not necessarily the same maximum intensity.
Yeah.
Again, keeping in mind this is normalized to the host star. Okay.
Yes. Boom, boom. Same general pattern.
Yeah.
Right?
Same general pattern.
Brighter in the top right, and then
middle
and point sources.
The maximum difference between that extended starry case and the fully illuminated zone at that substellar point is now only 21 parts per million in units of the stellar intensity. But if you look carefully, you'll see that the fall off for our numerical approximation is different than the fully illuminated zone, where that 50% contour is further away from that substellar point than the fully illuminated zone or any of the others.
Yes, quite. Okay.
That pattern will continue as we look at figure 8 for TRAPPIST-1. TRAPPIST-1d, I should say. There's more than one planet there.
That's true.
So this is just looking at TRAPPIST-1d.
Okay.
All right. You'll notice, first off, that maximum is very, very small.
Yeah.
At just over 0.7 parts per million. And if you look for that black dashed line, you'll see that it's very close to that
way out here.
That spherical cap where we would have longitude of like 90 degrees.
Yeah.
The fully illuminated zone takes up almost the entire hemisphere facing the host star.
Interesting.
That plane parallel array approximation looks pretty good.
Yeah.
It looks like a very good estimate for the fully illuminated zone. But what we don't get is any information in the penumbral zone where there is some light.
Yeah. Okay.
You'll also notice that the 50% contour for the starry method looks a bit more like the 50% contour for the fully illuminated zone, I-full, that analytical solution, than the numerical integration used in this paper in the middle left.
Right.
And when I first saw this, I was very curious as to why. What is going on? And This is why in another few figures, we're going to look at what happens when you vary the number of point sources used in your integral, which I believe in all of these figures was 25 points.
Okay.
So not a lot.
Not a lot.
What happens if we use more or less? We're going to get there. Before we do, though, if we look at figures 9 and 10, we're going to simplify a little. Instead of looking at entire intensity maps, we're going to look along the intensity equator, which for our coordinates and where we've placed the host star is at latitude 0.
Yes.
Just go around.
Yes, I'm with you.
This makes it easier to do some subtractions. All the subtractions, they're color and line style coded, given in that legend there. The vertical lines, we have a cyan dashed vertical line that marks the end of the fully illuminated zone, the beginning of the penumbral zone for this planet, which is Kelt 9b.
Yes.
And then the black dashed vertical lines mark the end of that penumbral zone and into the unilluminated zone where we receive no light. Cool. This is important because it helps guide our eyes. The fully illuminated zone eye full bit is only valid between the cyan lines. Correct. All right.
Yep, I'm with you.
Looking at some of these subtractions, the biggest thing I notice is the one between the extended source model using Starry and the extended source model using equation 11 is the greatest. And it follows a pattern of being greatest at that substellar point and falling off as you move away.
Symmetrically.
Also, the magenta dashed line for the difference between the extended source case using the angle of incidence and the foreshortening. And then that analytical solution for eye full is pretty close to 0 all the way through the fully illuminated zone. And we have that little inset in the upper left to try to see just how close to 0 it is. And it's pretty close throughout. Finally, another thing I think is worth focusing on is that numerical solution, I extended cosine psi, cosine theta prime, and I plane, which is the cyan dash dot line.
Yes.
And we'll notice that it's not a huge difference within that fully illuminated zone or that hemisphere facing the host star. But in the penumbral zone, we get some more interesting features.
Indeed.
That spike is at 90 degrees longitude on either side, where the plane parallel array case just drops to 0.
Yes.
Because there's no light on the anti-star side. So in some places, the extended source case, we end up with more light than the plane parallel array approximation. This includes at the substellar point and the anti-star side of the planet. But we get less light than the plane parallel array case in some regions of the penumbral zone. There. And a little bit ahead of it too in the fully illuminated zone.
Yeah, true. Okay. Interesting.
Now, those differences are small. They're on the order of 15 or so, 10, 15 parts per million. So the question is, will this matter when we calculate things like reflected light or in the context of modeling things like atmospheres and climates?
For example.
Yeah. Moving forward, we have figure 10, where this is mostly a sanity check, honestly. We have Kelt 9b analogs. So we've kept the planet size and star size the same, and we just vary the star-planet separation.
Oh, okay.
Yeah, we want to make sure everything goes to the same thing, that plane parallel array case, as we increase the star-planet separation. That dashed vertical line is the value for the star-planet separation in units of R star given in table 2.
Yeah, not the actual, so to speak. Yes.
The actual.
Yeah.
I always want to be careful. It's like, is it?
Well,
it's good.
Inferred. Okay.
And you'll see that the differences really disappear for large star-planet separations.
Yep.
I think this also, in plots like this, can help us determine for what types of exoplanets do we need to really think about this. Now, this is the intensity specifically at the substellar point,
Sure.
because it's the largest, therefore perhaps the most interesting.
Indeed. Okay. No, I like this plot. It breaks it down into two very nice regimes. So
Yeah.
where it matters and where it doesn't.
And you can also see other features too, like how quickly the different models get close to each other, like the extended source model in cyan for starry, and the extended source model using just the angle of incidence in the dashed dot red.
Yes.
They get close to each other faster than the starry model gets close to any of the others.
The other ones, right?
Yeah.
Overlap, which they should. Okay, good.
Yeah. And at the substellar point, we'll also see that the point source and the plane parallel array approximation are basically the same.
Right.
And also very close to I full. At least for Kelt 9b. Yes, the black one.
Yes. Yeah.
Yeah.
Okay. Good. 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 Good.
All right. So the next big thing to talk about is what happens when you vary n, the number of source points. We've got two figures that look at that. The first one is gonna be figure 11. We're going to look at all three planets at once, which means we're not going to use intensity maps because that would be too much.
Okay.
So we're going to look along that intensity equator because everything's symmetric according to cosine gamma prime anyway. Now, on the left, we have the extended source using starry. And on the right, for all three planets, we have the extended source using equation 11. Top row is Kelt 9b. Second row is Kepler 91b. And finally, we have TRAPPIST-1d on the bottom. The different colors on the right, all of the dash dot lines are numerical models for different values of n. I full is that solid black line. It's kind of thick. And we're kind of looking for what values of n is our output close to that black line.
Right. Which, to remind, is the analytical.
Is the analytical, correct. Now you'll notice that n equals 1 is pretty close across the board.
N equals 1, a little debatable integration there, but okay.
Yeah. Treating it as a point source.
Yeah.
That's what it really turns into.
Yeah.
But doing that doesn't give you any information within the penumbral zone. It doesn't let you look at any sort of extended source illumination. So if you look at that like blue dashed line, it goes to 0 first.
Yes.
So you lose all that interesting bit between that fully illuminated zone and where some of the other integrations go to 0. And we can see too that green dashed line of 25 is pretty good for Kelt 9b on the right.
Yes.
Also pretty good for Kepler 91b, but not as close, perhaps indicating why our intensity maps weren't as visually similar.
Right.
And then for TRAPPIST-1, it's definitely not as close as the starry method on the left.
Yes.
And we start again wondering why. Now, in the starry code, they make some approximations treating the size of the planet as being small compared to the star-planet separation, which is probably a pretty good guess for TRAPPIST-1d.
Right.
So I think by making that assumption, the numerical integration done in starry built up fewer numerical errors for each point that it was using. And that's what might be panning out here.
Okay.
So going into future work a little bit, previewing that is making the code more precise, using some different methods of numerical integration.
Okay.
Finally,
relaxing that assumption.
Yes.
Okay.
We look at differences in figure 12. Same idea. Kelt 9b is at top, Kepler 91 in the middle, TRAPPIST-1d at the bottom. Now we're looking at subtractions at the substellar point. We're varying n across the horizontal.
Yes.
We have the subtraction for starry on the left
Very
to the
good.
fully illuminated zone analytical solution. And then on the right, equation 11.
Yes.
Our goal
Ah,
is to have that dashed line, which is the average of all of those differences shown, be close to 0, if not 0.
yes.
We also would like our dots, those subtractions, to approach that line and it be near 0.
True.
And we see that it pans out fairly well for Kelt 9b
Yeah.
as well as Kepler 91b. It's clearly not 0,
It's a little bit
but
lower in here. Mm-hmm.
the method used in this paper with equation 11 is closer to 0 than the starry one, but that is not true for TRAPPIST 1D.
Right.
All right. Now,
Okay.
another thing about this plot is the filled dots, I believe, are even numbers of source points, and the unfilled ones are odds.
Oh.
And I did this because I wanted to see if there was a pattern between even and odd being
Yeah.
closer to 0 or not, because I was wondering as you change the number of source points, where they're distributed near the limb of the star is different. Right? Sometimes you get more near the limb than with other numbers of source points, because we're doing this on like a square. Well, it's a flat circle. Flat sphere is a circle,
Uh-huh.
and then popping it out. Instead, we could potentially distribute our points equally on,
Yes.
for equal area instead of on a circle.
Oh,
Does
interesting.
that work better? That's another thing to explore.
Indeed. No.
Could we distribute the points on the star in some way that depends on the point you are on the planet? Because right now, when we're distributing the points on the star for our integration, some of them are just set to 0,
Okay.
right? They don't emit light toward the point, or they're cut off by the horizon.
Oh, they don't count.
Yeah, they don't count.
They don't count.
But we could instead maybe figure out where the points ought to be ahead of time and put them where they would all be visible and do the integration. There's a lot of different methods we could end up using, and these plots, 11 and 12, persuade me that that's a really good next step.
Okay.
Is nailing down a strong numerical integration method.
So is the current integration method, is that a quadrature scheme?
Basically, yeah.
Okay.
Yeah.
Okay, with you. Yeah, otherwise I don't see how you get this odd even effect. So yeah.
Yes.
And one
yeah.
other minor question, just so I get
Sure, yeah.
sense of the efficiency here. So for any of the ones you choose, what is the relative cost in going from, let's say, 50 to 300 points?
That's shown in table 3 if you scroll down a little bit. Perfect
Okay.
question. I love it.
Great question.
Not very much. Now
Very
this
good.
only goes up to 69 points on the left. So we see the number of source points. This is subtraction at the substellar point for
Yes.
the various left methods shown in the top of the column, and then computation time in seconds for the starry method on the left, and using this model on the right. Now, I think it's really important to point out that all of the times for starry include initializing the maps and then calculating the intensity.
Okay,
The
so
starry initializes maps by first setting the number of source points. So you do have to do that first. And because that was included as part of making this table, I included that as part of the time.
Yeah.
But you can see the time is very short to run these calculations.
Okay.
1/10 of a millisecond.
Yeah.
And this was with just a computer I had at home. It's nothing fancy. It
That
really
is not a
isn't.
supercomputer right there, people.
No. And for now, it doesn't need to be.
It doesn't need to be.
Yeah. Yeah, I hope that answers your question. It
Yes,
doesn't,
thank you.
adding more points doesn't add too much to the time.
So you could go to 3,000, 30,000.
I have done this with at least 1028.
Okay.
And it worked fine. It took
Yeah.
a little longer. That's when I started to actually notice how much time it was taking. But before then, it was very quick.
Okay. Cool.
Yeah.
Very cool. Okay.
So where do we go from here?
Let's say that.
Calculate if, yeah.
Let's
I
say
think the only equation left is equation 29.
Oh, the foreshortening. Yeah, yeah.
Yeah. So this is just how one would approach calculating the reflected light. IP is whatever intensity you want in terms of eta and phi, which are angles on the exoplanet, right? You multiply that by some sort of reflection intensity distribution or albedos or what have you in the form of rho.
Yeah.
And then cosine gamma accounts for the foreshortening of the part of the exoplanet visible to the observer. You integrate over the balloon that is receiving light and is visible. There you go.
Nice.
It ends up being piecewise, and I have done this calculation within the fully illuminated zone in the past, and it's not analytical. You end up having to do it as an approximation. And I think it's another reason for wanting to use these numerical integrals. So you're going to have to start using approximations no matter what eventually.
There's always.
Yeah.
Cool.
Yeah.
Very, very cool. Jenn, I want to thank you so much for walking us through your very lovely article. Beautiful.
Well, thank you.
Beautiful. We were kind of chomping at the bit there a couple of times. so let me go ahead and ask. Where do you think we go from here given the published article? Is there a different exoplanet packages, different integration methods, comparison to other observed systems, and so on? So where do we go?
I think all of the above there.
Okay.
My first goal really is getting this integral to be a bit faster, because if we want to eventually incorporate it into something like ExoNest to characterize planets using light curves, it needs to be fast, because we do that many, many times to search the whole parameter space.
Right.
As fast as this is, it wasn't fast enough to do that sort of thing.
Okay.
Depending on how precise you want to go. So I'm working on that over this summer with a colleague here from Susquehanna University, Joy Upton Azam. And from there, I also want to apply this to global climate models with things like Rocky 3D and everybody that works on that.
Right.
I think those are the two next big goals. And also, of course, applying it to other hot Jupiters, getting a really good sense of what sort of planets does this matter for? How many points do we need? What's the cost benefit on including hyperillumination versus just using the plane parallel ray approximation?
Right. When does it matter? Yes.
Certainly, I think it matters for small star planet separations around 3 stellar radii.
That was in the plot. Yep.
Yeah. That around 3 seems to be what I see for a lot of different like hot Jupiter analogs.
Rule of thumb.
Yeah.
Let me go back to the making it faster and faster and faster. Is it possible to tabulate these? So you create one large grid and then you just do the interpolation and it won't get any faster than that.
That's one of the approaches that might be taken. I'm a physicist at heart. I do a lot of the physics part, and I'm getting more and more into the coding because I really have to. And doing this as a table, I think, is probably going to be the way to go.
Well, okay, I'm just throwing ideas. Anyway.
I think one of the questions would be if you're doing a search of parameter space to try and determine the planetary radius, if that's part of your model.
Yeah. Right.
Where the extent ends depends on that planetary radius. So you would have to have a lot of
fairly fine grid
maps put together, and I don't know how fine how many slices
many
in the
do you need?
parameter space you really need, how close
Exactly.
together
How
they
many do
need
you
to be.
need
I
for
don't know
sense of
yet.
accuracy? Yeah, that's a whole
Yeah.
game, but yes, yes.
Even looking at applying this to climate modeling, there's a question of whether or not the grids they use for the
Yeah.
installation are fine enough to even pick up on this difference from hyper illumination, or do
Right.
we have to use a finer grid, something finer than a
The
degree
bulk.
by a degree or
Ooh,
so?
ooh.
Yeah, it might be very fine in order
Yes.
to probe this, or you could potentially have a grid that is more fine near the terminator
Okay.
or the pole, wherever you're interested in, and less fine elsewhere.
Other options there would include a subgrid model for those things instead of, model what's going on in there as opposed to adding a grid, but TBD, it'll be very
Yeah,
exciting.
we'll see. There's lots of different approaches, and we're going to try and find the best
Cool.
one.
Cool. Well, I really look forward to seeing this develop over the next couple of years. It'll be really exciting to see. So very cool. And that will do, everyone. And I hope this made your astronomy day a little more illuminated. And we will see you on the next one. Bye-bye.